In today's class, we're going to look at some ideas from chapter 12, which involves the structure and properties of solids, and also do a little bit of review as we head towards the final exam. Within this slide, we see different images for solids in the world around us. They are truly diverse: diamond, butter, copper, glasses, the technology that you're probably carrying around, all different types of solids. Don't get me wrong, I think that things like liquids are important. I like to eat and drink. I also value breathing the air. But beyond that, almost everything in our world that's interesting, it's a solid of some kind. So in today's class, we're going to learn more about um, their wonderful variety. I mentioned the final exam. Here's some ideas as we head towards the final. First of all, for a learning strategy, I'm a big fan of the 3 points that are listed on the top of the slide. As a student, you need to know the learning objectives, so you've got to be looking at the right material. You want to authentically test yourself to identify strengths and weaknesses. And the third, transform instructional materials. That means instead of passively looking at slides or the textbook or videos, you have to take that material and make it your own. Writing summaries of the content is one way to help make it your own. What to expect for the final exam? Well, it's going to be longer than the previous midterms. The content is drawn pretty evenly from all of the different chapters. A previous midterm might be 25 or 30 questions. On the final exam, it'll be that same content, but half as many questions. We also have some new ideas in chapters 10, 11, and 12, but a lot of the exam comes from earlier content in the course. If I think about key skills that will lead to success on the final, number one would be stoichiometry. We saw stoichiometry introduced in chapter 3. Then we used it in chapter 4 with solutions. We connected it to energy in chapter 5. We connected it to gases in chapter 10. Stoichiometry, really important skill that you need to have to do well on the final exam. We've also been using the periodic table again and again. When the course began, we used it to identify metals and nonmetals and the common charges that different ions have. And we've done a lot with it since. We've considered electron configurations. We've considered properties of the particular atoms, like electron affinity, ionization energy. We used it to construct Lewis structures. And from Lewis structures, we've been doing other skills like applying VSEPR theory to determine whether the molecule is polar or not. And we're now seeing that's relevant for chapter 11. So key skills that cut across a lot of different chapters: stoichiometry, the periodic table, Lewis structures, and applying VSEPR theory. Within chapter 12, we have just a few targeted learning objectives. We want to understand the structure and properties of solids, contrast crystalline and amorphous materials, and understand what a unit cell is. On the topic of solids, solids are going to be found within a phase diagram. That's the topic that we saw within chapter 11. So consider this generic phase diagram. The axes are the pressure and the temperature. What I'd like you to do, identify where are the solids, liquids, and gases found on this phase diagram. We see arrows going back and forth to indicate phase changes. What are those phase changes? And which of them are exothermic? Give that a try. Here we see in the phase diagram where the solid, liquid, and gas phases are. The different phase changes that we have would be melting and freezing, as we're thinking about transformations between solid and liquid, or liquid and solid. Between the liquid and the gas, we have vaporization and condensation. Between the solid and the gas, sublimation and deposition. The exothermic ones I list there in red: freezing, condensation, deposition. Those would all be examples of exothermic phase changes. When I'm bringing up the idea of exothermic and energy, Let's consider what topics we had earlier in the semester related to that when it was first introduced in Chapter 5. So some key skills that we need from Chapter 5 as we think about the final exam. We want to have a conceptual understanding of terms like heat, work, internal energy, and enthalpy. We did some calculations involving specific heat and calorimetry. We had provided data that we'd use involving bond enthalpy and standard enthalpy of formation. We did calculations involving Hess's law, and we connected enthalpy changes to stoichiometry. Those are all in Chapter 5. We added a few more ideas involving energy later in the course. We looked at energy as it was connected to properties of atoms. The equation E equals h nu from Chapter 6 involves energy. In Chapter 7, we had ionization energy and electron affinity. Energy within molecules pertaining to bonding was discussed, and we looked at bonding models. And more recently, when we're looking at the energetics acting between molecules, be they intermolecular forces or phase changes, all of these have to do with energy as well. So energy is going to be an important topic for us. When we're thinking about the bonding in solids, we have some insights already. Ionic solids are something we've discussed as this set of cations and anions that are attracted to each other throughout the solid. For molecular solids, those are different. Within those, we have discrete molecules that we often have linked together by intermolecular forces. When it comes to ionic solids, this is not the first time we've seen them. Ionic solids have been discussed throughout the semester. We began early in the semester with naming ionic compounds. We looked at the energetics leading to the formation of cations and anions, did rankings involving the size of cations and anions, and also analysis of the lattice energy. Let's use this as an opportunity to practice a few of these. This slide lists 4 ionic compounds. What I'd like you to do is name them, determine which one has the largest lattice energy, and what would be the electron configuration for the silver plus that I see listed in that final ionic compound. For the naming, we have lithium fluoride, magnesium carbonate. Carbonate is a polyatomic anion that we need to know. Aluminum oxide, and silver nitrate. Silver nitrate has another polyatomic anion. The one with the largest lattice energy, that would be the aluminum oxide. I'm looking at the charges first, and aluminum's +3, oxide's -2. That's the greatest combination of charges. For the silver nitrate, silver is one we have to be a little bit careful with. Silver itself has an anomalous electron configuration, just like copper above it on the periodic table. It would be the krypton core, 5s1, 4d10, and to make it silver plus, we would remove from the highest principal quantum number, that's n equals 5, to make it 4d10. Molecular solids, again, those are described by having discrete molecules that are often linked to each other by intermolecular forces. We've done a lot with discrete molecules. We've looked at naming particular molecules. On midterm 3, their analysis with Lewis structures, VSEPR predicted geometry, and polarity. A lot of different ideas and skills all grouped together there. We had 2 different approaches for describing the bonding. Valence bond theory, that's the one with hybridization, and molecular orbital theory. We also classified molecules as strong, weak, or non-electrolytes and considered their behavior as acids or bases. More recently, we've been looking at them in terms of intermolecular forces. This question considers several of those ideas. So we have melting point data listed for 3 different molecules, and we're asked to try to explain the differences in the melting point. Why would the melting point for the C2H5F be greater than the melting point that I have for C2H6? Why would the CH3OH have the highest? CH3OH, what's the name of that? And is it a strong, weak, or non-electrolyte? Let me show you my work here. So the first thing that I'd have to do is, let's see if we can make a sketch. So here would be Lewis structures for all 3 of those. If I'm comparing these 2, They both are going to have London dispersion forces. And the one at the bottom would have greater London dispersion forces because I see that fluorine is going to be larger than the hydrogen. I think that the C2H6, that's going to have a very small dipole moment because the electronegativity differences between carbon and hydrogen quite small. Whereas I think the one at the bottom, that's definitely going to be a polar molecule. So to explain the stronger attractions, I would be using both London dispersion forces and the fact that that has dipole-dipole interactions. Where does the top one fit in within my comparison? I think that I have London dispersion forces in both cases, and in fact, I have greater London dispersion forces in this bottom molecule. So that can't be explaining why the top one has a higher melting point. What makes it different? It's going to have hydrogen bonding. So I would use that within my explanation. CH3OH, that's methanol. That's one of the simple organic compounds that we need to know. And methanol would be a non-electrolyte. When we're thinking about solids and the bonding within them, we want to contrast crystalline and amorphous materials. Crystalline solids are arranged where they have a very regular pattern. This would be an example for the mineral quartz that has the formula SiO2. Notice how it has a pattern that's being repeated again and again. That's a characteristic of all crystalline solids. An amorphous solid lacks that repeating pattern. Here is a very common glass, SiO2, same formula as quartz. It also has bonds within it, but notice how it doesn't have that repeating pattern. That's what makes it an amorphous solid. An amorphous solid, a glass, is as if you've melted the initial solid material, and then before it could adopt the particular ordering, you quench it or lock in that disorder. That's what an amorphous material is. In terms of the ordering, we find that solids have a repeating pattern, a repeating shape that takes place again and again. These shapes that we have that repeat again and again, or tile to fill up the entire surface area that we have, are called unit cells. The unit cells must be a particular shape that we can repeat again and again to fill up the entire space. You could take a square, for example, in 2 dimensions, again and again, and it would fill up all the space. If you were to take that and think about it in 3 dimensions, we again find that there are a certain number of shapes that we could repeat again and again, and that can be used to fill up all the space and construct the solid. All of the different types of solids that we're going to encounter that are crystalline, whether they're ionic, molecular, metallic, or covalent solids, all of these are going to have a unit cell that is repeated again and again. If it is a crystalline solid, it's going to have a unit cell. An amorphous material, a glass, in contrast, does not have a repeating pattern, so it does not have a unit cell. Now, we've talked about the bonding already in ionic solids, where we have cations and anions, and molecular solids, where we have discrete molecules and intermolecular forces. We're going to add to that 2 different types of solids, metals that have metallic bonding and covalent network solids. Both of these are different than our ionic solids and molecular solids, and they also have quite different properties. So let's switch now, and instead of considering the bonding, let's consider their properties. Metals are characterized as having the ability to conduct electricity. They're often strong, but they're not brittle. That means you can change their shape. Think about a metal fork. You can take your metal fork, you can bend it, you can twist it, you can squish it, and it still stays all stuck together. So you can adjust its shape even though it might be difficult to break it apart. If we're thinking about ionic solids have high melting points, high boiling points, but they're not something that you can readily change their shape of. In contrast, they are brittle, and they would usually break along planes. Also in contrast to metals, they are electrical insulators, not conductors. If we're thinking covalent network solids, They're often extremely hard. A diamond is an example. That's what comes to mind when I'm thinking of covalent network. And semiconductors, an important form of technology in our everyday world, those also involve covalent network solids. And then finally, molecular solids. These are often soft with relatively low melting points. Where do these different properties come from? Well, let's start first with metals. If I'm thinking about a metal, a characteristic is that those particular elements have low ionization energies. We've seen how they often become cations. But what if you have only just that particular element present? We could have something where we are forming a cation, but the electron there, instead of being attached to an anion, instead becomes a property and able to move throughout the solid itself. So instead of having it just stuck on one particular anion, it's now delocalized. One model that could describe this is this sea of electron picture. We have this whole distribution of cations, and the electrons now are found as the glue that's in between right here. So a given electron, it would be attracted to more than one set of positive charges. This is a really powerful model. This explains quite a few of the different properties. Okay? The electrons are free to move throughout the space in between. Free to move means that they would be able to conduct electricity. We're also able to change the shape. If you were to begin to deform this and alter the position of the cations, it's not breaking the bonds. We still have connections with the electrons found throughout the space in between that can hold it together. So this is a great model that could predict the electrical conductivity and also the fact that you can change the shape. That's very different than an ionic solid. Ionic solids, what comes to mind with that would be things like gemstones. We have this alternating pattern of cations and anions, and that gives rise to some very different characteristics. They have high melting and boiling points, like a metal might, but you can't readily change their shape. You can't twist or turn an ionic solid. They're brittle, and they often break along planes. And that's what we see as a characteristic of the gemstones. This image right here I really like that shows what's going on. We have an initial array of cations and anions. If you were to apply a force and begin to offset that, instead of having the alternating patterns of cations and anions, now we have it where they begin to align with each other. And that would create repulsions, not attractions, and that's what causes it to cleave or split away. Knowing how you can apply pressure along particular planes, that's what a jeweler does when they're creating these different shapes with gemstones. Really fascinating. Electrical insulators, we have negative charges, our electrons, but they're not free to move throughout the solid. Instead, they're localized on the anions. That's in quite contrast to what we saw with the metals. So this would make them electrical insulators, not conductors. When it comes to ionic compounds and their behavior in water, important topic for us in Chemistry 1210, also in Chemistry 1220. We've done a lot with this. We've been working on naming polyatomic ions. That was back in Chapter 2. In Chapter 4, we looked at their description as strong electrolytes. When we have the ions, we applied solubility guidelines to be able to write precipitation reactions and identify spectator ions. In Chapter 4, we looked at the concentration of solutions, being able to make dilutions, apply solution stoichiometry and titrations. And we even saw when we have an acid and base reaction, one of the products is an aqueous salt. Earlier, we used this particular PhET simulation to see how an ionic compound would dissolve in water, how it would dissociate, how we would have cations and anions, how the concentration would change. We used units of molarity to describe the concentration. If we connect this with Chapter 11, we can now consider how if we add a salt to water, it breaks apart because we have these ion dipole interactions, where we have cations and anions now surrounded by these polar molecules. This is going to be where Chemistry 1220 begins, looking at the energetics for interactions like this. Molecular solids are in the world around us. Sugar, carbon dioxide, water, all examples of molecular solids where we have discrete molecules. Let's connect this to an idea that we've been practicing in Chapter 11. At room temperature and pressure, carbon dioxide is a gas, H2O is a liquid. Which intermolecular forces could be used to explain this? This format of the question, this really sets up well for what you might see on a final exam. So select all that apply. Which intermolecular forces explain that observation? The first thing that I do when answering this is to ask, which has the stronger intermolecular forces? One's a liquid, one's a gas, so the liquid has the stronger intermolecular forces. So the intermolecular forces are stronger in the H2O. So which intermolecular forces do I have in H2O that are stronger than in carbon dioxide? The dispersion forces, I think those are stronger in the carbon dioxide. So that can't be part of the explanation. However, carbon dioxide is a nonpolar molecule, and it certainly doesn't have hydrogen bonding. So the best answer here is that dipole-dipole interactions and hydrogen bonding in H2O explains why it is a liquid and carbon dioxide is a gas. With molecular solids, we're interested in the intermolecular forces between them. Those intermolecular forces can include things like hydrogen bonding. That's what's being shown here. This is the unit cell for a crystalline form of H2O solid, a form of ice, and we notice that we have this particular alignment due to the hydrogen bonding. An important physical property that we find for molecular solids is they oftentimes have a low melting point. They have a low melting point because we're not breaking bonds within the molecules. Instead, we're changing and overcoming the intermolecular forces. So we're typically going to preserve the molecule, we're just going to change the arrangement. And it's a lot easier to do that than to break the bonds within the molecule. Going back to Chapter 7, we had some data provided for us. We saw that some of the data that was provided was the property of an atom. The ionization energy, that is a property for an individual atom. When we're thinking about the atomic radius, that was also the property of an individual atom. If we're thinking about melting point, however, that is not the property of a single atom. The atom itself doesn't melt, the atom itself doesn't boil, it's the arrangement that changes. If we think about this particular heating curve, we could consider as we heat up ice as a solid, then we could consider what does it mean to melt it, to heat up the water, to boil the water, and then to heat up the gas. As I look at this, I would say that as I'm adding heat, the temperature is increasing as I can increase the kinetic energy of the particles. But the fact that I have a plateau, even though I'm adding heat, tells me that on the plateau, I'm changing the potential energy. I'm changing the position. Now, within the figures here, what about the density? What do you think about that? Is that the property of an atom or a collection of atoms? To answer it, let's consider diamond. Diamond is an example of a covalent network solid. Within this case, we have covalent bonds, just like we would have discussed earlier in Chapter 9. But now, instead of terminating with a discrete molecule, they run continuously from one atom to the next to the next. So those strong covalent bonds, they're now a network that runs throughout the solid instead of having discrete molecules. That's what a diamond has. They tend to be quite hard and have high melting points. Graphite is another crystal structure that is entirely carbon, but it ends up having very different properties. Notice within its arrangement, we have a given carbon atom bonded to 3 different neighbors, but then it's forming a sheet that is separate from another sheet, which is separate from another sheet. So we no longer have strictly covalent bonds, we have covalent bonds within one of the sheets, but not acting between them. This leads to really different properties. Diamond would be a covalent network, whereas graphite, because it has these sheet structures, is quite different. A pencil is something that as you apply pressure, it breaks off into these particular sheets, and that's certainly different than the properties of a diamond. The density I list here is also different. So this tells us that if we're thinking about density, density is not the property of the atom itself. It relates back to the arrangement of those particular atoms together, because after all, carbon as diamond and carbon as graphite have different densities. Now, if we were to look at this, let's connect it to valence bond theory. What's the hybridization of carbon in diamond? What's the hybridization of carbon in graphite? Give that a try. As we look at diamond, we have this tetrahedral that's repeated again and again. If it's a tetrahedral, it's sp3 hybridized. In graphite, I see three neighbors making it trigonoplanar. That would be sp2. Now, we've seen notation like this before. Carbon is graphite, reacting with 1/2 O2, 2H2 to form methanol. Do you remember what we did with that notation? That was writing a standard enthalpy of formation reaction. And that was referring, in this case, to carbon when it was with this graphite structure. So we want to be able to write standard enthalpy of formation reactions, and we want to be able to use them. And when I say use them, back in Chapter 5, we had data provided in two different ways. It could be within a data table involving bond enthalpies, or it could be one where we have specific standard enthalpy of formation data given. We want to be clear how to use each one. With standard enthalpy of formation data, we can use our expression products minus reactants, whereas with bond enthalpy, we're going to consider the energy that it takes to break the bonds minus the energy that it takes to form them, because bond breaking is endothermic and bond formation is exothermic. Next class, we're going to finish off Chapter 12. We're going to look more closely at unit cells and also spend a little time practicing some ideas from Chapters 4 and 5.